Well, hello and welcome back to Physical Geography. This week we're doing Chapter 16. And we're talking about water, and the fancy term is fluvial. So, have you ever heard the term effluviant or effluvient? Fluvial, it means water. So, let's start talking, as we always do, about the human sphere and floodplains. And floodplains are areas near major rivers that are flat and flood very easily, hence the name floodplain. But if you look at human history, major cities, in fact, civilization begins in this area here in Egypt and what is currently Iraq and Iran and Kuwait. This area was the floodplains of the Tigris, the Euphrates, and the Nile River. And if you look at ancient China, the rivers there, the Yangtzes and the Wangho, those rivers, their floodplains were the sites of the first cities there. And in India and the Indus and Ganges River, people settled near rivers. Now, why? First of all, usually near rivers, the land's flat, so it's easy to build on, therefore desirable for settlement. When rivers flood every year, and we'll talk about this, they leave behind soil, which is very fertile, natural fertilizer. So it's flat land, easy to plow, lots of crops can be grown. And then the rivers allow you to transport goods by boat quite easily. So all of these factors kind of combine to make floodplains one of the earliest sites of human settlement, even though they flood. So people were willing to put up with this. And this is kind of one of the things we'll talk about is why do people do this to this day? I mean, you think about cities on major rivers like New Orleans and St. Louis. I mean, we're even on a river too. So let's start off by talking about stream patterns, right? And by the way, just so you guys know, stream is just the word for any kind of channel of which water flows downhill. So it could be 1 inch wide, it could be as wide as the Mississippi River, which is a mile and a half at some point. But it's just a channel of water, and it usually flows downhill by gravity. Unless someone can show me water flowing uphill, that'd be pretty cool. Now, when we look at a map, we often look at what we call watersheds or drainage basins. And this is the area on a map where one stream drains all of it. And what I mean by this is if you are in the drainage basin of the Mississippi River, that means that any water that falls from the sky will eventually make its way into the Mississippi River. So in other words, that whole area is drained by the Mississippi or any other streams that flow into it, right? And in that we have what's called a trunk stream, the main stream, and then branches. I'm going to show you a map that'll make much more sense. But a tributary is a smaller stream that joins a larger stream. So let's look at the Amazon River, for example. This is the Amazon River, this large black line. This is the trunk stream, the main Amazon. All these little blue lines are separate rivers called tributaries that join into it. So it kind of looks like a tree branch, right, or a leaf. Here's the main stem and the smaller branches. And that's kind of the idea. Lots of smaller rivers get together, they connect, they join, they eventually merge and form one big river, the Amazon. And by the way, the Amazon River is so big that some of its tributaries are bigger than the Mississippi River. So it's a huge river. Now, the second thing is the drainage basin. Right here, everything within this line, this entire chunk of land, which is almost half of South America, any rain that falls within this area will eventually make it to the Amazon River. So this is the drainage basin of the Amazon River. And the mouth is where the river stops, in this case, the ocean. So the mouth of the Mississippi River is the Gulf of Mexico, the mouth of the Amazon is the Atlantic, and so forth. Now, we're going to talk next, how do these lines get drawn? In other words, how does water that falls here go this way, and water that falls here go that way? And it's topography. There is no limit to how big a basin can be. It all depends on the actual elevation of the land. And look at this model. Here you've got two rivers, one here and one here, right? And these are two drainage basins. This is that divide. So this line right here, drainage divide, if we go back, right, is this. This is the drainage divide, this line right here. Any rain that falls on this side of the hill eventually goes down here or down here. So this is the drainage basin. Conversely, any rain that falls here goes here. So what defines the size of drainage basins are these ridges, right? So they could be small, they could be huge, it all depends. Come back. Now, again, here's another one right here. Sometimes we give these divides specific names, and one of the most common ones is the continental divide. In the case of the United States, here's an example. Any water that flows here goes to the Pacific, and any water here goes to the Arctic. That's a major difference. Let's show you what I mean. Here's a map of the United States, right? This is one of the continental divides, this black line right here. And that little map I showed you is right here. Any water that falls here on this side will eventually flow into the Pacific Ocean. But any water that flows on this side will eventually make it to the Arctic Ocean. Here's one, the Atlantic Ocean and the Gulf of Mexico. So here's that boundary right here. Okay? So you can see that there are several rivers in here, but they all empty into the same body of water. Now, even within a basin, you can have smaller sub-basins. So, example, everything that's colored in here is drained by the Mississippi River. This right here is the Mississippi River. It goes right here. The Missouri River is a tributary. You know it's pretty big. But you could actually look at just the area drained by the Missouri, or just the area drained by the Ohio River, because these are tributaries. So you can break up a boundary in any way. These are kind of basically like subsections. Okay? But what's interesting is how this affects us. Let me go back. If I could zoom in, I wish I could. Chicago's right here. You'll notice that we are on a boundary. We're on a boundary between the Gulf of Mexico and the Atlantic Ocean. And this is the main reason that Chicago is here. Okay? This is a map of Chicago before the city was built. So this is prior to 1830. This is the Des Plaines River. It's out in the western suburbs, which flows and eventually goes down to the Illinois River in the Gulf of Mexico. This is the north branch of the Chicago River, the south branch, which eventually flows into Lake Michigan. So Lake Michigan and the Great Lakes flow into the Atlantic Ocean, and the Des Plaines River and the Ohio and the Illinois River flow into the Gulf of Mexico. This was a subcontinental divide, a very, very shallow one. In fact, it's only about 2 or 3 feet taller than the rest of the land. You wouldn't even notice this. If you were driving from downtown to, say, Midway Airport right here, you wouldn't even notice it. It's very, very shallow. But for exaggeration, here it is. Here's Lake Michigan, the Chicago River. This is the subcontinental divide, and over here is where the Des Plaines River would be. Now, one of the first Europeans to come through the area noticed that if you were to dig a canal right here, you could shortcut all the way from the Great Lakes through the Chicago River into the Mississippi River system, and you would have an all-water route from basically the East Coast to the Gulf of Mexico. And back in the 1700s, that was the best way to get around. The European explorer was Father Marquette and Louis Joliet. He actually wrote a report to the King of France. They were the first Europeans to come through Chicago. And he said whoever controls the Chicago portage, this little break in the water route, would control North America. And that's why Chicago was here, because in the 1830s, we dug a canal right through that. And then now it allows trade to go through. So it was originally dug for trade, but today we use it also because, as we've talked about, Lake Michigan is where we get our drinking water. To stop pollution from the river entering the lake, we reversed it. Let me go back a shot. This is the original flow of the Chicago River. Any pollution here would get washed out into the lake. City fathers figured out if they dug that ditch right here, because this side of the divide is lower, gravity would force the river backwards. And today, that's what happens. The Chicago River actually flows backwards. So the river flows here this way. It used to flow this way. Now it flows this way. But this right here is the actual drainage basin of the Chicago River. Very small, but it does have one. Now, another one that you see not as often are internal drainage systems. These are rivers and lakes that do not flow to the ocean. So they are usually in the middle of continents, hence called internal. Okay? Usually what happens, these end up in areas that are dry or hot, and the water that flows there forms a lake, and it's usually a salty lake, like the Great Salt Lake or the Dead Sea. And the reason that these lakes don't get any bigger, with the rivers constantly putting water in them, is as the rivers put their water into the lake, the water evaporates. And what's left behind, right, is that salty water. So most of the time you'll see a saline lake. So it looks like this. This is a map of the world drainage basins. So let's look at North America. This green part right here, all the water drains to the Atlantic Ocean. This orange part, water drains to the Gulf of Mexico. And this blue part, the Pacific Ocean. You'll see right here, where this is Utah, Nevada, parts of Colorado, any water here doesn't make it to the ocean. It actually ends up in the Great Salt Lake in Utah. There's one here in the middle of Asia, which is the Caspian Sea. There's a few in Africa and Australia as well. But in Israel, there's one, the Dead Sea. The River Jordan actually ends up in the Dead Sea. It's like a miniature ocean. It's only about maybe 20 miles across and 100 miles wide. The water flows in and then it evaporates and it gets saltier. This is the saltiest body of water around. It's, I think, roughly 10 times more salt than the ocean. There is so much salt, it makes you float easier. As you can see right here, you cannot sink. Now, I kind of alluded to it, but if you look at a map of stream patterns, the tributaries and the trunk streams, it looks kind of like a tree trunk or a leaf. There are different patterns they form, and the most common one is the dendritic drainage pattern. And dendritic refers to trees. So let me show you what that looks like. This is the dendritic drain pattern. Here's the main stem and the tributaries, and it looks like a tree or a plant. That is the most common one you will find. There are a few others, not to worry about it too much, but I like to point them out. I love this one. It's called the deranged pattern. You don't see this orderly pattern. This is usually after a landscape has been changed by a glacier, which we'll talk about in a couple more chapters. And then the other two that I really want to mention are the radical and centrifugal drainage. If you have a mountain like a volcano, all the water is going to flow off of around the edges, almost like spokes. So it looks almost like an eye. But if you have a crater or a large deep depression, the water will all flow towards the middle. I wouldn't worry too much about rectangular drainage or trellis drainage. They are available, but we're not going to talk about it too much. I'm going to pause this right here, and we will come back with the next part in just a moment.